I was just waiting. There we go. That's what I was just waiting for the number to asymptote, and it's still increasing. Okay, never mind. So, hi everybody. I'm just going to get started. Welcome to the U of T Physics Colloquium. So today we're very lucky to have Professor Katherine Freese from the University of Texas Austin / Stockholm University as our speaker. Katie is a world-renowned theoretical particle physicist / theoretical astrophysicist / theoretical cosmologist. And as you can guess, she's made many important contributions across this broad scope of areas. She's a central figure in the study of dark matter, dark energy, and inflation, and their connection to cosmology and astrophysics. Prior to her current geographical superpositions, she held faculty positions at MIT and Michigan, and she's received many honors and awards, including the Simons Foundation Fellowship and the Lillian Field Prize, and she's a member of the National Academy of Sciences. So we're very excited to have her here today and to tell us about what dark matter is and isn't. And because of the online format, I ask that you please save your questions for the end when we'll have time for a discussion. So thanks very much, and take it away, Katie.
Well, David, thank you so much for the invitation. And I always want to remind people where we stand in terms of big picture. So throughout human history, people have wondered where we come from, where we're going, what the universe is made of, and everybody had creation myths. And the remarkable thing is that over the last 100 years, starting with Einstein's relativity, well, we have our own creation story, the Big Bang, but the difference is that we actually got it right. If you think about it, in human advancement, that is huge, huge, and it's very exciting. So we've had enormous progress over the last century, but even more since the turn of the millennium, some of the big questions about the universe have been answered. We know the geometry of the universe, we know the energy density, we know the age of the universe, but many questions remain, and one of the big ones is, what is the universe made of? So I'm going to start right away with some of the most influential data in teaching us about the universe, and that is the Planck Space Telescope. This is a picture of the sky in the microwave, so back from 380,000 years after the Big Bang, so almost all the way back to the Big Bang. And this is from the size of the hot spots and cold spots in this data. You can see the hot spots in orange and the cold spots in blue. We learned about the geometry of the universe. And we know that the size of these things, the prediction was, if they are 1 angular degree in scale, then that would tell us that the geometry of the universe is flat. And yes, you can see this peak at exactly 1 degree. So yes, the geometry of the universe is flat. And by Einstein's relativity, we also know how to connect the geometry with the mass and energy content of the universe. And so that answer is 10 to the minus 29 gram per cubic centimeter. So that's, I would say, is the energy density in outer space. And I want to contrast that with on Earth, where water on Earth has a density of 1 gram per cubic centimeter. So in terms of the big picture, we know what the geometry is and the total mass and energy content of the universe. And from the Planck satellite, you saw there was not just that one peak at 1 degree, but there are a bunch of the other peaks also tell us an enormous amount about the universe. So what we learned from that there are the 6 basic parameters of the universe. This one tells you about the amount of ordinary matter in the universe. That's from the height of that second peak. And from a combination of the peaks, we learn the amount of dark matter in the universe. And so I'm going to draw that instead as a pie picture. But before I do, this happens every time that I use this. The slides jump. So forgive me, it's going to happen again. Anyhow, so this is again the microwave background data. This is an earlier NASA satellite, the Wilkinson Microwave Anisotropy Probe. And we have in here Stephen Hawking's initials. But so seriously, from these data, we also know what the big picture of the universe is. And so we know that the ordinary matter only makes up 5% of the universe, whereas dark matter and dark energy make up the rest. So it is still a remaining question as to why the WMAP satellite, the earlier one, found 23% dark matter, whereas Planck has, as its best fit, 26% dark matter, and we still don't understand the origin of this discrepancy. But what we certainly know for sure is that the ordinary stuff only constitutes 5% of the universe, and we're left with understanding most of the constituents of the universe. So this dark matter problem is one of the longest outstanding problems in all of modern physics. It is 80 years old. It dates back to the 1930s, originally actually to a Swedish scientist named Knut Lundmark, and famously also Fritz Zwicky, a Swiss scientist working in Pasadena. And this is a picture of Zwicky, who looked at the Coma cluster, observed the galaxies inside the Coma cluster, and saw that they were moving too rapidly. So the galaxies are, the motions are determined by the gravitational pull of the other stuff. And based on the stellar light that he saw, these galaxies were going way too quickly. So he proposed dunkle materie, or dark matter, as the explanation. Or the word dark here simply means it's not stars, it doesn't shine. So you've probably all heard this stories about Fritz Zwicky, but I'm going to tell you anyway. So in his book, he called his colleagues spherical bastards, because they're bastards no matter what direction you look at them from. So I don't think that you wanted him as your PhD advisor. There was a lot of activity after that, questions about how ubiquitous this is, and it was really the work of Vera Rubin in the 1970s that led to consensus that the dark matter problem is really there, because she found it existed in all the galaxies that she looked at. And specifically, the tool used to do this are rotation curves of galaxies. So this is a galaxy that at the center of the galaxy, we move out a distance r, and we observe things moving around the center. This could be gas or dust or stars. And the velocities of these orbits are determined by the amount of mass interior to that radius. So this capital M of r is the mass interior to the radius. And from the virial theorem, the speeds of these orbits scale in this way with the mass, and obviously larger mass causes faster orbits. So this is a picture of the kinds of measurements made by Rubin and Ford, starting at the centers of galaxies and moving out with radius of the orbits, how fast things are moving as you move out. Now, based on the stellar material that they knew about, this is what would have been expected. So based on the disks of galaxies, that's what would be expected, the stars and so forth. But instead, they found these data points up here are flat rotation curves. And in order to explain that, you can add in a halo of dark matter and it solves the problem. I'll use our galaxy as an example of what this looks like. And so at the center of our galaxy, there is a supermassive black hole. And of course, I have to mention the Nobel Prize in Physics that just was given for black holes. And half of it was for the discovery of this supermassive black hole at the center of our galaxy to Andrea Ghez and Reinhard Genzel. And that black hole weighs 4 million times as much as the sun. Then there's a pinwheel structure stemming out from that, and that's where the stars are. So for example, the sun is along one of these pinwheels, these spiral arms. But if you take all of this stuff, which is the light that we see when we look out into the sky at the Milky Way, and you turn it on its side, well, that's now what we call the disk. And the sun here is 25,000 light years or 8 kiloparsecs away from that central black hole. And so we don't notice this black hole at all. In fact, the mass of the galaxy is 10 to the 12 solar masses, where the black hole is 10 to the 6 solar masses. Taking that spiral disk structure, that is now embedded in a dark matter halo. This is obviously an artist's rendition of what the dark matter looks like. So that was the first piece of evidence that something had to be there pulling on things. That's evidence for the existence of dark matter. Then another one is using Einstein's gravitational lensing. So as I'm sure you all know, mass bends light. So the idea here is that whatever the dark matter is, whether it be a massive compact halo object or anything else, it takes stellar light and bends it on the way to our telescopes. So we would assume the star is in a different place than it actually is if we didn't know about the dark matter in the way. But then we would notice, aha, there are multiple images of this thing because the light can go in multiple directions. And we would notice that the light is sheared. So although dark matter doesn't give off light, you can detect its existence by watching it bend light. It is fun that there's an app written by a Michigan graduate student, Eli Reichhoff, that you can get on your phone that has the correct equations of gravitational lensing. So go try it on yourself. So my students did that. And as you lend yourself more and more, it gets more and more interesting. Now this is actual data from Hubble Space Telescope. And here you have distant galaxies lensed by dark matter between those galaxies and us. There's an awful lot going on in this slide, and I don't even know all the details, but you can certainly see there are sheared multiple images going on here. And based on that, you can reconstruct how much dark matter is between us and those distant galaxies. So when you do that, you can get pictures like this. I have to say that this one is not the same object as the previous slide, but it gives you the same idea, and it's also from Hubble Space Telescope data. So this is the density distribution of the dark matter that was providing the lensing. So you see these peaks are galaxies. So there's a lot of galaxies in this. This is a cluster of galaxies. There's lots of galaxies. And there's also dark matter in between the galaxies. So not only do the galaxies have dark matter, but the clusters do as well. So in addition to the rotation curves and lensing, there's an object, a famous object, the bullet cluster, that is thought to really show us the existence of two separate types of matter. What's going on here is that you have two clusters of galaxies that are colliding with one another. And so after this initial collision, the ordinary stuff, the gas, which is found in pink because it gives off X-rays, so that gets stuck in the collision. So for example, if you and I collided, we have electromagnetic interactions, we have strong interactions, we're not going through each other. And so that's exactly what happened to the gas. On the other hand, from lensing, we see a separate type of mass that did keep going. So when the collision happened, the dark matter kept going, and that's shown in blue, and we know about it from lensing. So what you can see here is a very different behavior of these two types of mass. So that's thought to be very strong evidence that there really are two types of mass. So I was mentioning, as proof that dark matter exists, we know this from rotation curves, from gravitational lensing, from bullet cluster, from many other things. And actually the best data that we have is what I showed at the very beginning, namely the peaks in the cosmic microwave background give us the best estimates of the amount of dark matter that we have. It's also interesting to point out that without dark matter, we could not exist. If you only had ordinary matter, then structure formation would be too slow. We wouldn't have galaxies yet. But dark matter can clump earlier. And so this is a simulation of how that happens. You have in blue shown, these are dark matter particles shown in blue. This is a simulation done with dark matter only, starting in the early universe. And so you can see the dark matter particles are spread out with not completely homogeneously. And as time goes on, they clump together until we reach the universe today in these simulations. And this matches our universe quite well. So these are long filaments of structure with the galaxies at the nodes or intersections of these filaments. And so again, in order for us to exist, we needed the dark matter to clump, and then afterwards, the ordinary matter could fall into the potential wells provided by the dark matter. So back to this pie picture, we're left with the question, what are these pieces of the pie? And I want to talk about the dark matter. So some of the earliest ideas, perhaps the ones you might think would be the most obvious, would be that hot gas or rocks or dust or lumps of hydrogen. And very quickly, it was proven that these things would have observational consequences that we don't see, so they cannot be the dark matter. Then before 2000, there were two camps. There were believers in the massive compact halo objects, which I'll talk more about in a minute. These would have been made of ordinary matter because at that point, it wasn't entirely clear that you needed anything beyond ordinary matter yet. We didn't know that yet. Or it was the believer in more exotica, really. So beyond standard model physics, WIMPs, axions, and so on. So we had the machos versus the WIMPs. And I participated in both sides of the debate. So these massive compact halo objects could have been faint stars or substellar objects, because as you go to lower mass, there's more and more objects, but these only add up to 3% of the galaxy, which we use theoretical and observational evidence to constrain that. Now, stellar remnants are also interesting. So, but again, there's a lot of, they would have a lot of observational consequences from their progenitors. And so white dwarfs can still be 15% of the mass around us, but you cannot solve the dark matter problem with these things, as was also then shown by microlensing experiments. Okay, so baryonic dark matter is not enough, and we do have to go to new ideas. There are many, many candidates out there, and I've just listed some of them, some of the better motivated ones. So neutrinos, they would have been great because they exist, but the problem is they're too light. So they would ruin galaxy formation. And besides, we know that this is the contribution neutrinos would have. This is the fraction of the total mass in the universe in the form of neutrinos. So 50 neutrinos would have given you exactly that closure density of the universe. But instead, the sum of neutrino masses adds up to roughly 0.1 eV, which means neutrinos contribute 0.5% of the mass of the universe. I do want to talk about neutrinos, though, because cosmology can have such can teach us so much about them. So we know from observations of neutrino oscillations, we know the differences in neutrino masses. So of the 3 active neutrino species, we know that the electron-like and muon-like one are separated by the smaller of this, by this amount, whereas those are separated from the tau neutrino by this amount. So, but we don't even know which is the lightest of these. But what we learned from oscillations experiments is only the mass differences. So the reason neutrinos are so exciting is because they're the only piece of physics that we have that is absolutely known, that's beyond the standard model of particle physics. Now, to get the absolute scale of neutrino mass, there's many different approaches, including tritium beta decay experiments, neutrinoless double beta experiments. But what I want to focus on is what cosmology can tell you. So it is a combination of cosmic microwave background data together with large scale structure that gives you these very strong bounds. So here I plotted the neutrino mass versus the Hubble constant, because it turns out there's degeneracy. So for example, from cosmic microwave background data, you have this larger curve, but then as soon as you add in large scale structure curve, it narrows you down. And my group in Stockholm, we did quite a lot of work on this, and we showed that the bounds are the sum of neutrino masses less than 0.15 eV. And that ended up in the particle data group's review of particle properties, which was great fun. Now the Planck satellite has slightly stronger bounds, less than 0.12 eV, but you get the picture. These are strong bounds, especially because going back to oscillations experiments, the lower bound on the sum of neutrino masses is bigger than 0.06 eV. So we're really narrowing it down. This lower bound versus this upper bound, you're really getting there. I also wanted to mention that the role neutrinos plays in large scale structure is it suppresses small scale structure. So going to the right is you're going to the power on smaller scales, and you can see that's what neutrinos do because they stream out of structures. Another thing that's interesting is that everything I've told you about neutrinos so far assumes a standard lambda CDM cosmology, in other words, cold dark matter with the cosmological constant. But we examined actually the case of an arbitrary dark energy. As long as the equation of state is bigger than -1 at all times, it can be dynamical. Then it turns out the bounds on neutrino mass are actually even tighter. So the cosmology of neutrino mass is on very solid grounds. The upcoming CMB experiments are going to do even better on this. And my group has joined these 2 experiments, SPIDER at the South Pole, which also Barth Netterfield is part of, and the Simons Observatory, and Renee Lozek is very visible on this project. The Simons Observatory started with a donation from the Simons Foundation. It's sitting in Chile in the Atacama Desert, 17,000 feet above sea level. And it is waiting for the pandemic to end. So first light guessed at around 2023. And it's going to get neutrino mass down to sum of neutrino masses 0.04. I'm also personally, the reason I originally joined, actually, I want to know R from inflation because it tests inflation models, including my own. So in any case, neutrino mass is close to being measured for these 3 active neutrinos, and it is cosmology that plays a major role in this business. Now, beyond the 3 active neutrinos, it is possible that there is a 4th neutrino, sterile neutrino, which does not participate in the standard model interactions at all. It does mix with active neutrinos, so the sterile can decay to the active ones, or it can turn into them as it travels along. And this is an interesting dark matter candidate that I'm not going to talk much about. There is even a potential signal of 3.5 keV neutrinos in X-ray data. But I did want to mention, I'm going to mention throughout when people in my group make contributions. And so this is a paper combining all the bounds on sterile neutrino mass that weigh less than a keV, in case you are interested in taking a look at that. So back to this question, what is the dark matter? Well, I've talked about neutrinos. I also think primordial black holes are very interesting candidates, and Florian Kühnel, my former postdoc, has written a lot of reviews on this. So the reason it's getting a lot of attention is because the question is, did LIGO detect primordial black holes? Was that the origin of the LIGO data? Well, this is a deviation from what I'm supposed to be talking about, but this is a paper we wrote like 2 weeks ago, so I got to say something about it, which is LIGO has now found black holes where they shouldn't exist. It found black holes in this mass gap, okay, and there aren't supposed to be any black holes between 50 and 140 solar masses. Well, we have an explanation for that because the reason this happens is because the precursors of these guys should blow up with parent stability supernovae, but it turns out you can stop that if you add nuclear energy to the stars. So back on the dark matter question, let me show that slide one more time. I'm going to focus on the things that are the most highly motivated. A lot of people are doing a lot of work beyond this these days, such as with light dark matter, and it's all very exciting, but I want to focus today on the ones that are the most theoretically motivated. And the reason I say that is because for both WIMPs and axions, cosmologists didn't invent them. In fact, these particles already exist in physics models of particle theory in order to explain other problems. So axions, for example, arise in the Peccei-Quinn solution to the strong CP problem. The theory of strong interactions has a problem, and you automatically get axions in the solution to that. And they're very light, but still non-relativistic. And Luca Visinelli, my former postdoc, has written a nice review on this. And on the experimental status, here's the axion mass. Here's the axion coupling to photons. And this is, in yellow, are the theoretically motivated particles as far as helping with QCD. Now, people these days are not interested only in the QCD axion, but more generally in axion-like particles or ALPS. And you can see an enormous experimental effort going into all of this. So in the ADMX experiment, maybe if they find something, maybe they'll find QCD axions. I do want to focus for quite a while now on WIMPs. These are weakly interacting massive particles. And as I said, they don't have stronger electromagnetic forces, but of the 4 forces, there is one left, and that's the weak force. So that is what we postulate that WIMPs have, and they weigh about 1 GeV to 10 TeV. There's 2 reasons why they're favorite candidates. One of them is that we can calculate how many of these things there are. For the ones that are their own anti-partners, we can calculate their annihilation in the early universe and figure out how many are left today. And the only ingredient in this calculation is the annihilation cross-section, and for that we use weak interactions. And if you do that, you end up with the right WIMP abundance. Some people call this the WIMP miracle. Another reason people are interested in WIMPs is because they automatically exist in particle theories such as supersymmetry. And here, for every particle that we know, there is a partner, a supersymmetric partner, and these are unstable, the heavier ones decaying to the lighter ones and so forth, until you get to the lightest supersymmetric particle, which may be the dark matter. Oh, and the lightest supersymmetric particle is a WIMP. So the well-motivated is one thing, but we have to go and prove that they exist. So there's a three-pronged approach to this. It's the same Feynman diagram, just read in different ways. And I'm going to talk about these three approaches, as well as I hope I have time to mention dark stars, which is my baby. So the first search for WIMPs, the first way to do it is at the Large Hadron Collider at CERN. So here we have proton beams that are traveling in opposing directions underground, and where they collide, you put detectors. So I have a few pictures. This is Fabiola Gianotti. She was of the Atlas detector. She was the spokesperson for the Higgs searches and is now Director General at CERN. These are giant experiments, as you know, with a person looking rather small. And Atlas has a Toronto group. And I asked Pekka Sinerva just to send me a few pictures, and here they are. Peter Higgs in front of the CMS detector, the other giant detector that's useful for the things I'm talking about. And sure enough, the Higgs boson was discovered at 125 GeV. Then the second major goal of the LHC is to search for new physics, such as supersymmetry and dark matter. So here you'd have two protons colliding and producing a chain of decay products. At the end, you'd end up with this lightest supersymmetric particle leaving the detector and showing up as missing energy. Then from these side things, you'd get jets. So that combination would tell you that you've found something like supersymmetry, but that has not happened yet. So the minimal supersymmetric standard model has 105 free parameters. So if you want to put things on one plot, you look instead at the constrained minimal supersymmetric standard model, which assumes all the fermions and all the bosons at high mass are the same. In that case, there's only 5 parameters, and you can put it on a plot like this. And you have to be up and above these solid lines. Old data, but the basic picture is unchanged. So I wanted to make a few comments. One is that we knew before the LHC started that SUSY might just be, that you might miss SUSY with the LHC, and you have to go either to higher scale, or you have to go beyond the constrained models. And then I also wanted to say that even if SUSY is found at the LHC, we still won't know how long lived the particles are. So to see if it's dark matter, we need other approaches. And I think this is a very exciting proposal that David Curtin was one of the people to start. This is Methuselah. This is outside the standards. It's sitting on top of CERN, on top of the Large Hadron Collider. And so it's a search for long-lived particles. So here are the Atlas or CMS detectors, and then you look for what came out of them. So I think that's a really cool idea. You should ask David about that. Now, a second way to search for WIMPs is direct detection experiments, which take advantage of the fact that there are WIMPs in the galaxy. So here's a nucleus, and the WIMP scatters off of the nucleus, depositing a small amount of energy, a keV of energy. Very, very hard to detect these things. Very low count rates, 1 count per kilogram per day. Well, this leads me how did I get into dark matter? And so students, I had a great advisor, David Schramm. He got me into it. So he was one of the founders of this whole field of particle astrophysics. Find a great mentor. Anyhow, so and then we did some of the very earliest work on WIMP, on whether or not you could look for WIMPs by building detectors. And so I did the Feynman diagrams of particles scattering, WIMP particles scattering off of nuclei, and David added in the velocity distribution of the halo as being a Maxwellian, which turns out is pretty damn good. And Andre was the guy that, well, he's a character. I met him in Israel, and he'd written papers on neutrinos to do this. And then, of course, elastic scattering is the same thing for WIMPs, and it works better. So here is the Maxwellian distribution for WIMPs, and I really just wanted to mention the typical particle speed is about 270 kilometers per second of WIMPs moving through the galaxy. So these detectors must be deep underground. Here, for example, is Snow Lab in Canada, 2 kilometers below ground. And the reason for that is you have to get rid of the cosmic rays that would come in, but the cosmic rays can't get through the Earth, so they can't get to your detector, and they would really overwhelm your signal. So since we did those calculations, now there's a whole worldwide effort that got started. Well, this is today. Oh God, I wish this would stop jumping. I just don't know what to do. Okay, I'll try something else. No, okay, anyway, so this is a worldwide effort. And the only people that have found anything are here, the DAMA experiment in the Grand South Tunnel outside of Rome. And I want to describe what they found. This is so the sun is moving around the center of the galaxy, which means that effectively we are moving into a wind of WIMPs. It's kind of like when the rain is coming down and you're driving, it looks like the rain is coming at you. So, but then on top of that, you have the Earth moving around the sun. And we realized that would give you an annual modulation. In other words, the count rate would go up and down with the time of year, with a minimum in December and a maximum in June. And over many, many years of data, that is exactly what DAMA finds. I have to correct this. It is a 12 sigma signal. They definitely see annual modulation. Yep, more and more data keep seeing the same thing. Now there's two problems. One is that they won't let other people see their data, which is very confusing situation, very unusual. And then the other one is that other experiments have null results. But comparison is difficult because experiments are made of different detector materials. And not only that, we've got some very interesting characters leading these experiments. So for example, here's Juan Colliar saying, "I'm a Spaniard caught between two Italian women." So this is an old picture, but it's nice, it gives the idea. So if I want to compare the DAMA positive results, and that experiment is made of sodium iodide crystals, with the negative results from other things, I need to put in some additional theory. So in this particular picture, spin-independent WIMPs are shown, which means the cross-section scales as with atomic mass squared. So if you divide out the atomic mass squared, then you end up with DAMA, consistent here with 10 GeV WIMP mass. I wanted to mention this is the WIMP mass on this axis and the cross-section for scattering on the y-axis. So DAMA is consistent with these two regions in green, but then the Lux and Xenon experiments tell you you have to be down here below those curves. So it looks like things are ruled out. But that's not necessarily true because, again, DAMA is made of sodium iodide and these guys are made of xenon. So here are more recent results. It's the same thing, but it's just more recent data. And as far as future experiments, this is what is planned and is going to push into competition with neutrino signals, actually. So this is from the sun or atmospheric and supernova neutrinos. And in particular, going to low mass, super CDMS, and your faculty member, Miriam Diamond, is participating in this. They're going to be able to go to low mass very successfully. That's made of germanium. So what's interesting lately is that the xenon 1-ton experiment actually has an excess at a few keV in the number. This is the events versus energy. And the question is, have they discovered dark matter or not? And this is only a 2 to 3 sigma excess. So I think probably the answer is no, but it isn't, but people got excited because although most particles don't work, they don't fit the data, there is one that does, and that's the QCD axion. So that's kind of amazing. So events per energy from the axion, you would expect this is the right spectrum. So, oh my God, have they found QCD axions? Well, the problem is the way this would work is they would be coming out of the sun. So in the sun, you would have bremsstrahlung producing axions, which you would see in the xenon detector. But if the sun can produce axions, so can other stars. And so you'd have the stellar cooling of white dwarfs and other stars would mean that you wouldn't have the white dwarfs and horizontal branch stars that you see. And so the stellar cooling bounds rule out this explanation in terms of the axion. So most likely it's a statistical fluctuation, but it's gotten people excited. So back on the subject of DAMA, the good news is that there are other experiments that are also using sodium iodide crystal that are now taking data. In fact, the cosine 100 experiment has 1.7 years of data already. And so this is the modulation amplitude versus the phase. And so they actually agree with DAMA, but this is 2 sigma, so it doesn't mean anything. But anyway, within 5 years, this experiment, which is based in Korea, is going to either rule out DAMA or agree with it. So that's an exciting future status. So the difficulty is we're comparing apples and oranges because detectors are made of different materials, but we do have more experiments coming up made of the same material. And on the theoretical side, people are working very hard, both with particle physics and nuclear physics, to try to explain how can you have null results in these other experiments and positive results in DAMA. Now, going to go even to more sensitivity, to go beyond, to compete with the neutrinos and still find WIMPs, one thing you could take advantage of is if you had a directional detector that could tell the direction the WIMP came from, well, then you would take advantage of the fact that there's 10 times as many events if you look in the direction of the WIMP wind as in the opposite. And so I couldn't resist mentioning some ideas we've had how to do that. So here's an idea for dark matter detection using DNA. So you can buy this from Illumina Inc. for 200 bucks. I mean, it's not radioactively clean. You're not going to build dark matter detectors out of it, but the technology's there. So this is a nanometer thin layer of gold with strands of DNA attached. When the WIMP comes along, it knocks a gold nucleus forward into the DNA, and it is the gold that breaks the DNA. And the beautiful thing about DNA is you can control everything. You can control, so you can figure out this was an A, C, G, da, 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 da. You can make millions of copies or billions of copies of these things. And so you can reconstruct the track that the gold came from, thereby telling you what direction the WIMP came from. So this effort has, on the experimental side, stalled. George Church, who's a famous geneticist at Harvard, has got some stuff in his freezer, but the experimental effort is temporarily stalled. We need physicists to join him. Another idea that we had is paleodetectors, and the idea here is, well, with the xenon detectors, we're talking about 1 ton or n tons of xenon liquid, giant things. But instead, what you can have is tiny rocks, but they've been accumulating signals for a very long time, for 500 million years. So the trick is to get ancient minerals from 10 kilometers below the surface of the Earth and look for the tracks that have been left behind. And in the modern era, the nano tools, you can identify nanometer tracks, and that's what makes this actually doable nowadays. So there is an experimental group starting to do that. Now, another way to look for WIMPs is indirect detection. And the idea, again, is the same dark matter annihilation that happened in the early universe gives rise to a chain of events, in the end producing neutrinos, positrons, or gamma rays. And there are experimental efforts to look for each of these annihilation signals. So positrons, gamma rays, and neutrinos. And the AMS aboard the International Space Station did find an excess of positrons, but it's clear it's not dark matter. So these guys showed that, well, if AMS is right, then for example, for the BB Bard channel, if you made positrons, you also made photons. And then Fermi should have seen more than they did, so you have to be below the blue lines. So the dark matter interpretation does not work. What is interesting, however, is that Fermi satellite towards the center of the galaxy does see a gamma ray excess, and we don't know what it is. So in fact, there's a residual near the center, very near the center of the galaxy, that could be due to dark matter annihilation, although pulsar explanation is also possible. So in the end, we have anomalous events in DAMA. We have anomalous events towards the galactic center. And so we'll see what happens. I do want to talk about a fourth way to search for WIMPs. As I said, this was our idea on dark stars. The idea is the very first stars to form in the history of the universe could have been powered by the same dark matter annihilation. So this was the three of us, me, Doug Spoliar, and Paolo Gondolo, who thought of this, and we discovered there was a cult film that predated us with the same name. And since then, many others have worked with us. So the basic idea here again is that the first stars could have been powered not by fusion, but instead by dark matter annihilation. It's very important to point out these are made almost entirely of hydrogen and helium from the Big Bang. Dark matter constitutes less than 0.1% of the mass of the star. So let me tell you the basic idea of how they form. At redshifts between 10 and 20, inside protogalaxies that weigh about 1 million suns, they're right in the dark matter rich center, you have a gas cloud that starts to cool and collapse en route to star formation. But as it does that, it pulls in more and more dark matter. And eventually the dark matter density gets high enough that you get annihilation going. And those annihilation, mostly E plus E minus and photons, mostly those annihilation products collide with the hydrogen, are trapped inside the cloud and heated up. So they get stuck inside this cloud and they turn it actually into a star. So this new phase of stellar evolution can last a long time. These are very unusual objects. They start by weighing about 1 solar mass, but then they grow by accretion. And the whole time they're really giant puffy things. The radius is about 10 times the distance between us and the sun. So they're very, very cool. No fusion going on there, no ionizing photons coming off of them. And so they can just grow to be larger and larger, up to 10 million times the mass of the sun and 10 billion times as bright as the sun, which means they are detectable in the James Webb Space Telescope, and we've made predictions for that. Another thing that is exciting about these things is that once the dark matter runs out, they turn into big black holes. And those could be seeds for the supermassive black holes that we have all over the place in the universe. So this is the HR diagram for these things, and this is what they look like in the James Webb Space Telescope. You really can see them, but I'm going to skip ahead and just show you some of the black holes that are very hard to understand any other way. Look at this, a redshift of 6 already has a 10 to the 10 million solar mass black hole. So if you start with million solar mass seeds of black holes, that could explain the one I just showed you, the ones in the centers of galaxies, and other objects that are very hard to explain any other way, or even more, a redshift of 7.5 and 800 million solar mass black hole. So I've talked about really 4 prongs of WIMP hunting, these 3 direct, indirect, and collider searches, as well as looking for dark stars. If WIMPs are low mass enough, for example, you'll see the dark stars before you'll see it in the other techniques. So I talked a lot about the unexplained signals in dark matter and briefly mentioned there's also, people argue about this one, is there evidence for a 7 keV sterile neutrino or MEV dark matter from X-ray data? There is a line, an unexplained line there. I don't know how much time I have left. I wanted to talk also about something that's that is new, which is using GAIA data to test the nature of dark matter. The GAIA satellite measures positions and velocities of 1 billion stars in the Milky Way. And if you're watching stars move around, well, their kinematics is determined by the gravitational potential of dark matter. So that is a good way to learn about the dark matter. So this is the resolution of these kinds of detectors as time goes on. So you can see, this is dating back to Hipparchus, and then down here, GAIA with 1 billion stars with the excellent angular resolution. So one of the things we want to test when I say the nature of dark matter, well, everything I've talked about is cold dark matter. So WIMPs and axions are both in that category. So that is cold dark matter. These are non-relativistic dark matter particles. And the simulations, assuming cold dark matter, make predictions that one can go test with data. And so one of these is that the centers of galaxies and clusters and so on in the cold dark matter scenarios should be cuspy like this. In other words, as you go left here, you're getting closer and closer to the center of the object. The density gets higher and higher. So this is what's expected from cold dark matter, but in some objects, observations seem to show they have a core. Now, the reason for that could simply be that baryonic physics has switched the cusp to a core, or it could be that cold dark matter isn't quite right, and we should be thinking about alternatives. So one of the things we've been doing is probing the nature of dark matter by looking at streams in the Gaia data. And so let me show you, the Milky Way has about 70 streams, and here's what they look like. Here's GD1, here's JLM, there's a bunch of streams in there. So there's more than one way to form streams. They could form by tidal stripping of dwarf galaxies, such as that's known to be true for the Sagittarius stream. Or it could be, this is the one we looked at, tidal stripping of globular clusters of stars inside subhalos. So globular clusters are dense old star clusters that weigh with the total mass of about 10 to the 5 solar masses. And the idea that we're looking at is that there's if this is our Milky Way, this is a this is a subhalo with a globular cluster orbiting around in it. And the subhalo gets accreted into the Milky Way. And in the course of being accreted into the Milky Way in these simulations, oh God, it just won't stop jumping. I'm not touching anything, I swear to God. So anyway, these globular clusters get shredded apart into streams, and this is in a simulation. So our work is only using simulations, and what we found is if you had cuspy subhalos, then the streams you get are broader than if you had chord subhalos. So what we're finding is streams coming from cuspy subhalos, which would correspond to cold dark matter, are wider physically and dynamically hotter than those from chord subhalos. All right, so then the question is, can you go and compare that to data? Well, the first comparisons we made using the GD1 and JLM streams would indicate a preference for chord subhalos, but we certainly are not claiming that yet, okay? But if that did hold up, then that would tell you that either you have to go beyond cold dark matter or there was baryonic feedback. Baryonic feedback is most efficient at 10 to the 10 solar mass subhalos. But so then gaps in stellar streams are also probes of dark matter. But since I'm running out of time, let me just give you a summary slide on different ways that Gaia can be used to test the cold dark matter hypothesis. So I focused on this one, question of what the stream widths can tell you about the centers of the subhalos that the streams came from. Gaps in streams, these are holes in the streams that some subhalos could have gone through them, and this you can learn from that. Then the shape of the Milky Way halo, well, cold dark matter predicts triaxial, and so that's another thing to look for. Also, subhalos that passed through the Milky Way disk left residual observable oscillations. And then also, while we're at it, some people in my group, people are trying to get better estimates of the local dark matter density, which turns out to be about 0.3 GeV per cubic centimeters, using a number of different techniques. So anyway, this is an ongoing effort using these new data of stellar kinematics from the Gaia satellite to learn about the dark matter. I think it's time for me to summarize. I think I'm right on time, in fact. So as far as neutrino mass, we know the answer is around 0.1 eV, and we're getting very close to really nailing it down using cosmology as one of the main tools, of course, as well as neutrino oscillations. Then as far as WIMP searches, it's interesting to speculate what's going on with DAMA, and cosine 100 is testing it. Then I mentioned dark stars, the first stars that could have been powered by dark matter rather than by fusion. And I only talked about WIMPs powering them, but we're also working now on self-interacting dark matter. That seems also to work as a source for dark stars. Axions do not work. And new ways to test the nature of dark matter with the Gaia satellite. So in the last, if you'll give me one more minute, I'm just going to tell a joke. I haven't said anything about the big beast here, the dark energy. The only thing we really know is, well, when we say matter, that means it's gravitationally attractive. So dark matter and ordinary matter, you attract things together, you make galaxies, you make clusters. Dark energy, on the other hand, is causing the universe to accelerate, so it has the opposite behavior. It's some kind of repulsive behavior that's not understood at all. So on the so here's this naive picture of galaxies accelerating apart from one another, and we don't know why. So on the theory side, there are, there's people are trying a lot of different things. And one of the questions is it a constant acceleration, or is there some time dependence behind it, or what's going on? And I'm just going to end with this joke, which is that in 2011 at the World Science Festival in New York, I was on a panel. So the three of us were discussing dark matter. And these three guys were discussing dark energy. So that's Eleanor Prelay, Glennis Farrar, Mike Turner, Saul Perlmutter, Brian Greene. And I said that there's only one thing we really know about dark energy. And so I spoke the truth. And on that note, I will end. And this is a book, a popular level book that I wrote about this subject. Okay, so that's what I was going to say today. So I think I'll stop sharing so that I can see what the people who are asking